right, guys, here I'm going to talk you through what we're doing in lab this Friday. I definitely think you should have read through the procedure before watching this video. So again, I'm going to recommend that you hit pause right here and go read the procedure before coming back to watch the video. All right, so we're going to talk about hydrates, and first we'll talk about their nomenclature really briefly. And hydrates are special molecules, or special compounds, I should say, that are kind of a mixture between ionic and covalent compounds. One of the most widely used hydrates is magnesium sulfate. Hepta hydrate. Okay, so you can see already that this is a mixture between ionic and covalent based on the nomenclature. We have magnesium sulfate. That's an ionic compound. It's an ionic compound because it has a metal and it has a polyatomic ion. And here's our covalent part. We're talking about hepta, which is one of the prefixes. So that's what I mean, that it's kind of a mixture between them. And what a hydrate really is a molecule, is a compound that has water just associated with it. You can't, well, you can. You'll see what we're going to do in just a little bit. But it's an ionic compound that also has water molecules that are associated with it. So this magnesium sulfate heptahydrate, going to the chemical formula, magnesium sulfate is MgSO4. Magnesium has a +2 charge. Sulfate is one of the polyatomic ions you just have to memorize, times 7 water molecules. That means for every 1 unit of magnesium sulfate, it has 7 water molecules associated with it. So let's do another one and go back and forth between them. I'm trying to think. Oh, this compound, I'm pretty sure exists. Sometimes it does exist, sometimes it doesn't. Oh, by the way, this little raised dot is really like a multiplication sign. So it's magnesium sulfate and then 7 water molecules associated with it. The CaCO3 dot, or times 10 waters. What's the name of that? Calcium carbonate, because that's named normal ionically. And that is a decahydrate. Okay, so now what we're going to be doing in lab is actually determining the formula of a hydrate. We are going to be determining how many water molecules there are for every one of the units before it. So this is going to be straight stoichiometry. We're going to be doing it 2 different ways. The first way is relatively straightforward. The second way is a little bit more complicated. But let me sort of walk you through what we're going to be doing the first way. You are going to take a copper 2 sulfate salt. Salt is just a generic word for an ionic compound, okay? So copper 2 sulfate is a salt. You are going to take its hydrated salt. You want to figure out how many waters there are associated with every 1 copper 2 sulfate. And in order to do that, you're going to take this salt. You don't know how many waters there are, and you are going to heat it. What that will do is drive the waters of hydration off of the copper 2 sulfate, and you'll be left with anhydrous. Copper 2 sulfate, anhydrous means it has the waters removed from it, and then the water will go away as a gas. So you start with the hydrated salt. You'll put it in a crucible. You'll heat it up, and you'll drive all of the waters of hydration off of it. And that's a balanced chemical formula. So the balanced chemical formula, as we know, gives you the mole ratios of things. And from that, we'll be able to determine how many water molecules are associated. But really what I care about right now is the nomenclature. When it has the waters associated with it, that's called hydrated. When it has the water molecules driven off, that is called anhydrous. So let's take a look at your first part of the Prelab. Here we go. So if we look and see what we're doing, we are trying to determine the numbers of waters associated with this copper 2 nitrate salt. So we weigh the crucible, and we know that the crucible weighs 12.155 grams. Then we weigh into it some of the copper 2 hydrate. So that has the waters associated with it. So that's what our next thing is. We have 12.9 grams. That's the crucible and the mass of the copper 2 hydrate. Then we're going to heat it up in our crucible, and after we heat it and cool it, we get a weight of 12.629 grams. And you're going to do it a second time at least, and you're going to heat it and cool it, and we got 12.63 grams. You do that twice to ensure that all of the water has been driven off. Just from these simple calculations, we can figure out what that X is. I mean, this is what we're really trying to solve for. How many water molecules are associated with every one copper 2 nitrate? So now if we go over here, we're saying, okay, let's do these calculations. So what is the mass of the hydrate that we put into the crucible? The mass of the hydrate is the mass of the crucible plus the hydrate minus just the mass of the crucible. 12.9 minus 12.155, 0.745 grams. Straightforward so far. And again, guys, this is going to be exactly what you're doing in the lab. So hopefully y'all are following along. Otherwise, lab is going to be particularly painful. Now, next up, we want to have the mass of the anhydrous. That's after we've driven the water off. And I say to use the lowest mass after heating. So the mass of the anhydrous salt, the stuff that is left over after we've driven the water off, is the one that's lowest minus the mass of the crucible. So that's going to be 12.629 grams minus 12.155 grams. That gives you the mass of the anhydrous. After we've driven all the water off, the anhydrous is what's left over. 12.629 minus 12.155. 0.474. Okay, so how much water was driven off? The difference between those two values. You started with the copper 2 nitrate that had water associated with it. You drove all of the water off. So the amount of the water that's been driven off is the difference between those two. So that's 0.745. That's the mass of the copper 2 nitrate and the mass of the water. Minus the mass of the anhydrous salt. That tells us how much water has been driven off. 0.745 minus 0.474. 0.271. Okay, now we're doing stoichiometry. I want to know how many moles of the anhydrous copper 2 nitrate there are. Remember the anhydrous, the anhydrous copper 2 nitrate is when there's no water molecules associated with it. So I'm going to leave this one for you guys to do on your own in order to go from the grams of the anhydrous to the moles of the anhydrous. You need the molar mass of that anhydrous, just the copper 2 nitrate, no waters associated with it. Okay, so I'm going to label this with a star. When you figure that out, the answer to the star goes there. This next one, moles of water. You know how much water? I'll put a circle here. Let me put a star here, what you're going to need for these things. Okay. You know how much water you had. Once again, you're going to start, this is where the circle is, with the grams of water. use the molar mass of water in order to convert it to moles of water. And that answer goes in right there. Last but certainly not least, the formula of the hydrate. What you do is you take the ratio. Oh my goodness. Oh my goodness. Sorry about that. In order to determine the formula, you want the ratio moles of water divided by moles of anhydrous. That should give you a whole number, like 2 or 3 or 4 or 5. That is the number of water molecules, and that will give you the name of the hydrate. So again, the moles of water I said was this red circle. The moles of the anhydrous I said were that star. So you take the circle over the star, that'll give you a whole number. That is the number of waters of molecules associated with it. So then you'll have copper 2 nitrate times however many that whole number is, water molecules. All right, that's the first part. So you're going to take it, drive off the water, figure out how many moles of water are formed, and then go from there. The next part is much trickier. So I'm going to walk through this with you again and show you what you need to do. I'm telling you that a hydrate of iron 2 acetate underwent analysis. 1.5 grams of the hydrated salt was dissolved in water to make 12 grams of the solution. The solution had a concentration of 0.691 molar and had a density of 1.27 grams per mil. There is an example directly in your lab procedure, so I'm just going to give you some hints on how to work this out. You want to determine the volume in liters of the solution from the mass of the solution. Mass of the solution and the density. Okay, so we want our answer to be in terms of volume in liters. And we want to go from the mass of the solution and the density. So I'm going to write this down again. You guys can figure this out. You have 12.10 grams of the solution. And you know that the density of the solution is 1.27 grams per milliliter. Use dimensional analysis to get your answer in terms of liters, of solution. Okay? Now go on to number 2. After you get the liters of solution, from the volume in liters, you're going to start your dimensional analysis here with the liters of solution that you figured out in number 1 above, and the concentration. The concentration is 0.691 moles per liter. Determine the number of moles of the anhydrous. So, for every 1 liter of that solution, you know it contains 0.691 moles of anhydrous. No water molecules associated with it. Iron 2 acetate. And I'm going to let you guys figure out what that chemical formula is. That'll give you the moles of anhydrous. Iron 2 sulfate. Next up, from the moles of the anhydrous, so what we just solved for in 2, from the moles of the anhydrous and the molar mass. You guys know how to determine molar mass. Look at the periodic table, add it all up. That'll give you the molar mass in terms of grams per mole. So every 1 mole of the anhydrous weighs some amount of grams. Again, that's for you to determine. This is grams of anhydrous. Now, this is the tricky part that students don't like. And really, you just have to read. From the mass of the hydrated. The mass of the hydrated is, wait for it, 1.5 grams. Right here. From the mass of the hydrated and the mass of the anhydrous minus mass anhydrous. Figure out how many grams of water there are. Now we're going to convert grams to moles using the molar mass. Grams of water from above. There's 18.02 grams of water in every 1 mole. You guys will have that memorized at some point in time. That'll give you the moles of the water. And then last but not least, moles of water divided by moles of anhydrous. So moles of water we determined in number 5. Moles of the anhydrous we already determined in 2. That ratio will give you some whole number. That whole number is how many waters are associated with one of the iron 2 acetates. So that'll give you how many waters of hydration there are. All right, good luck. If you have questions, please let me know. And I hope that lab on Friday will go easily. It's a tricky one. It's long and a little bit tricky. So if there are any questions on this pre-lab, please feel free to email me.